Welcome, everyone, to your final exam cram session for natural language processing. In this explainer, we are going to quickly cover the entire syllabus, breaking down all the essential concepts and technologies you need to know. My goal is to get you feeling prepared, confident, and ready to ace that exam.
So let's just dive right in with a big question that really drives this whole field. Can a machine actually understand you? Well, the short answer is not really. Not in the way a person does, anyway. Machines don't have consciousness, they don't have feelings. What they are incredibly good at is recognizing statistical patterns. They learn to connect words and phrases by analyzing just massive amounts of data. And this difference between real understanding and super sophisticated pattern matching is key to everything we're about to cover.
Here's our game plan for this session. We're going to build everything up logically from the ground up. We'll start with the basics, then walk through the NLP pipeline, the process that turns messy text into clean data. From there, we'll zoom in on words with morphology, then zoom back out to see how they form sentences with syntax. And finally, we'll see how it all comes together in some huge applications like machine translation, and of course, the big one, conversational AI. Let's get started. All right, let's kick things off with section 1. Before we can get into all the cool technical stuff, we have to get the basics down solid. What exactly is natural language processing? What makes it so incredibly hard for computers? And where did it all come from?
Okay, this slide gets right to the heart of the matter. The fundamental problem, the number one challenge in all of NLP, is ambiguity. See, our languages, like English, are flexible, they're messy, they depend entirely on context. One sentence can mean a dozen different things. But computer languages, like Python, they're the exact opposite. They're built to be precise. Every single line of code has one and only one meaning. The entire field of NLP, really, is just one long effort to teach machines how to handle all the messiness and ambiguity of our language.
And you can see how our approach to solving that problem has evolved over time. It started with big philosophical ideas like the Turing test and these early, simple, rule-based systems like ELIZA. They were clever for their time, but they were super brittle. You gave them an input they didn't expect, and they just broke. The real game changer happened in the 80s when the whole field shifted to a statistical, data-driven approach. Instead of trying to handwrite a rule for every single thing, we just started feeding computers massive amounts of text and letting them learn the patterns themselves. And that shift is what led us directly to the incredible neural networks and LLMs that we have today. Okay, exam focus time. If you remember anything from this first section, make it these 4 points. 1, NLP is all about letting computers work with human language. 2, it's got two sides, NLU for understanding or reading and NLG for generating or writing. 3, the biggest challenge, the one that never goes away, is ambiguity. And 4, the way we do it today is almost entirely through statistical learning on huge data sets. You should be totally prepared to see a question just like this, and here's how you nail it. First, you define ambiguity. Then, give a solid example. For syntactic ambiguity, that's about sentence structure, use the classic, I saw the man with the binoculars. Who has the binoculars? Me or the man? See? Ambiguous. For semantic ambiguity, that's about word meaning, use something like, the bank is closed. Are we talking about a river bank or a money bank? Providing clear examples like that shows you really get it. All right, moving on to section 2. Now that we've got the what and the why, let's dig into the how. We're going to break down the step-by-step flow chart that computers follow to make sense of language, the NLP pipeline. This right here is a typical NLP pipeline, and you've got to see it as a sequence. Each step builds on the last one. You start with something really basic, tokenization, which is just splitting the text into words. Simple enough. Then you might simplify those words with stemming or lemmatization, getting them down to their core root. Only after you've done that can you do part of speech tagging, where you label each word as a noun, verb, or whatever. And that step is essential before you can move on to parsing, where you figure out the whole grammatical structure. See how it builds? The higher level tasks at the end totally depend on the groundwork laid by the earlier steps. So the main takeaway here is that NLP is not magic. It's an engineering process. It's like an assembly line for language. You put messy, unstructured text in one end, and at each station it gets cleaned up, labeled, and structured until this beautiful, organized set of data comes out the other end that a machine can actually understand and use. This is a very, very common exam question. You should definitely be able to sketch out these steps in order and just write one quick sentence for each one. So for tokenization, you just say it's about breaking text into smaller units, like words. And for POS tagging, you'd say it's about assigning each word its grammatical category, like noun or verb. Easy points.
Okay, so we've seen the big picture of how we process a sentence. Now, let's zoom way in and put a single word under the microscope. This brings us to section 3, morphology, which is basically the anatomy of a word. The most fundamental concept in morphology is the morpheme. As it says right there, it's the smallest piece of a word that actually has meaning. The best way to think about it is like Legos. Take the word unhappiness. It's not one piece, it's 3. You've got un, which means not. You've got the root, happy. And you've got ness, which is the bit that turns an adjective into a noun. We just snap these morphemes together to build words. Now for your exam, this table is absolutely critical. You have to know the difference between these two. On one side, we have inflectional morphology. This is all about grammar. Think about adding an S to make a book into books. It's still a book, just a plural one. The part of speech doesn't change. But derivational morphology, on the other hand, creates a totally new word, often with a different part of speech. When you add ness to the adjective happy, you derive a brand new noun, happiness. So, to recap morphology, it's all about how words are built. Inflection is for grammar, derivation is for making new words. And remember, this can get really different depending on the language. English morphology is actually pretty simple, but in a language like Sinhala, it's incredibly rich and complex. One single verb can have tons and tons of different forms. Here it is, your classic exam question on this topic. You need a super clear 2-part answer. For inflectional, just say something like walk becomes walked to show past tense. For derivational, you could use read becomes reader, creating a new noun. Simple, clear, and gets you full marks. Okay, time to zoom back out. We've seen how words are built. Now let's talk about how we put them together to form proper sentences. This brings us to section 4, syntax, or what you probably just call grammar. So the main job in computational syntax is something called parsing. Here's how it works. A parser takes a sentence, and it takes a set of grammar rules. These rules are usually written down in something called a context-free grammar, which is just a fancy name for a list of rules like a sentence can be a noun phrase plus a verb phrase. The parser's job is to check if the sentence follows those rules and then to map out its structure, usually as a kind of tree diagram. I love the analogy on the slide. If syntax is the law, the parser is the officer who diagrams the sentence to see if it's legal. For your exam, make sure you've got this chain of logic down. Syntax is the big idea of sentence structure. A context-free grammar, or CFG, is how we write the rules down for the computer. The parser is the program that actually applies those rules. And this is super important, the parser can't do its job until the words have already been tagged with their parts of speech. It's another perfect example of why that NLP pipeline has to go in order. You could definitely see a question asking you to compare different parsing strategies. So first, you'd say a parser's job is to figure out the grammatical structure of a sentence. Then you'd explain the 2 main ways it can do that. Top-down parsing starts with the big picture. It assumes it's looking for a sentence and tries to break it down to see if it matches the words. Bottom-out parsing does the opposite. It starts with the individual words on the ground and tries to build them up into bigger and bigger chunks until hopefully it ends up with a valid sentence. Okay, we have covered all the core building blocks, how computers look at words and how they look at sentences. For our last couple of sections, let's look at how this all pays off in some of the most important applications of NLP, starting with machine translation. The story of machine translation shown in this table is basically the story of NLP in a nutshell. We started with rule-based systems, where humans literally wrote down thousands of grammatical rules. Then came the statistical era, where we stopped writing rules and started learning probabilities from massive amounts of translated text. And now we're in the age of neural machine translation, which uses deep learning models. The absolute king of these is the transformer architecture, which uses a clever trick called attention to figure out which words in the original sentence are most important for translating the next word. It's what powers the amazing translation tools we use every day. And that brings us to our final section, conversational AI. This is really where everything we've talked about comes together. Morphology, syntax, understanding, generation. It all has to work in harmony to achieve what is kind of the ultimate goal of NLP, creating a machine that you can actually talk to. Think Siri, Alexa, and of course ChatGPT. This is the cutting edge. So to wrap everything up for your exam, let's hit the highlights on applications. For machine translation, remember those 3 stages: rule-based, statistical, and neural. And know that we often use something called a BLEU score to measure how good a translation is. For conversational AI, remember it's a 3-part system. It has to understand you, manage the conversation, and then generate a response. We've seen these systems evolve from simple chatbots like Eliza into the powerful generative AI we have now. And I just want to leave you with one final thought, which brings us right back to where we started. As these machines get better and better at mimicking our language, the line between just matching patterns and actually understanding gets blurrier and blurrier. Okay, that's our cram session. Good luck on your exam.